Hallo, it's dumplet here. Here's an item on geometry. Three vertices of a cube are at the following coordinates in 3D plane: 7, 12, 10, 8, 8, 1, and 11, 3, 9. Find its volume. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, so we're asked for the volume of a cube. So obviously, before we get the volume, we need the side, because the formula for the volume of a cube is just the cube of its side. So we have to get its side, but the only thing that we're given are the vertices of a cube. Alright, so the cube has 8 vertices, and 3 of them are given. But the problem is, we are not sure how these vertices are oriented. So for example, let's just have a cube here labeled, the vertices labeled from A to H. We're not really sure where these points are relative to each other. For example, 2 of these points might be points A and B. So if I just take the distance between A and B, it might be the side. That's possible, but we're not sure. Now, the next possibility is they might be opposite along one face of a cube. It might be like points A and C. Or in the last possible case, it might be a space diagonal, or like, for example, points A and H. They might be exact opposite corners. So we are not really sure how to interpret these yet, because we're not sure of their relative positions with each other. So it is very important for us to try to take the distances between all possible pairs of points from these 3 before we make any conclusions, because we might be able to realize that, for example, we might be able to make the conclusion that, oh, for example, these 2 points, the first 2 points, the distance between them is the side, or it might be a face diagonal, or it might be the space diagonal. So let's try to take the distance between pairs of points before we make any conclusions. All right, so to get the distance between pairs of points, just like in 2D plane or in the Cartesian plane, we're going to use the distance formula. And here we have the formula, distance formula, in 2D plane. It's just the square root of the change in x, the square root of the square of the change in x plus the square of the change in y. Now, the only difference now is that we're in 3D space, so obviously there's an additional z coordinate. So accordingly, there is a version for the distance formula in 3D space. So we're literally going to add the square of the change in z. Again, we can use the Pythagorean theorem to help us prove this one, just like how the Pythagorean theorem is also responsible, or the reasoning behind the distance formula in the Cartesian plane. All right, so let's try to take the distance now. The distance is equal to the square root of change in x, so the difference of 7 and 8, that's 1. 1 squared is just 1. Change in y, 12 and 8 have a difference of 4. So 4 squared, that's going to be 16. Then lastly, for the change in z, 10 and 1, they have a difference of 9. 9 squared is 81. Alright, so the distance is equal to the square root of 1 plus 16 plus 81. Working out the maths is going to give us 98. And we know 98 to be 2 times 49. 49 is a perfect square. It's 7 squared to be exact. So we can put the 7 out of the square root, and only the 2 will remain in the square root. So the distance between these 2 points, it's going to be 7 square root of 2. Alright, let's try to check the next pair of points. So 7, 2, 10, and 11, 3, 9. Same formula, the distance is equal to the square root of the square of the change in x. Change in x is 4, so 4 squared, that's 16. Change in y, 12 and 3 have a difference of 9, so 9 squared, that's 81. 10 and 9 for the z for the square of the change in z. Difference of 10 and 9 is 1. So 1 squared, that's just 1. So it's just the same triplet of values, just like in the previous example. So I think they would have to be square root of 98, and again, it's going to be 7 square root of 2. All right, pretty interesting. They have the same distance. And let's move on to the last pair of points, 11, 3, 9, and 8, 8, 1. So the distance is equal to the square root of change in x is 3, so 3 squared, that's 9. Change in y, that's 5. 5 squared is 25. change in z is 8. 8 squared is 64. And if we work out the sum, 9 plus 15 plus 64, you're also going to get 98. So interestingly, the distance, these three vertices of the cube that we are given with, they are the vertices of an equilateral triangle. So these three vertices, if we join them with line segments, it's going to be an equilateral triangle. So let's try to analyze how is this possible. For example, knowing that these 3 points form an equilateral triangle, it is already impossible for any of these points, any pair of these points to, for example, it's impossible that 2 of these points, if I connect the points, it's going to be a side, because there is no way for us to have an equilateral triangle with all 3 distances, or like the distances between the points, being the side. You guys can verify this on your own, but it's not possible. For example, if we have AB, then it's possible that the next segment would be C, but the third side, it's impossible to form a third side with the same with the same distance of just the side of the square. So it's actually impossible. And you guys can work out all the possibilities, and eventually you'll realize that the only possibility for an equilateral triangle to be formed by the vertices of the cube is when all three sides that form the equilateral triangle are the face diagonals. So the diagonals of 3 of the faces of the cube. So I'll draw a quick example here. For example, in the top face, so focusing on the top face, this one, EB is a face diagonal. And focusing on the front face, BD is a face diagonal. And focusing on the left face, DE is a face diagonal. Although it doesn't look equilateral, but these 3 are the face diagonals of the cube, so all these 3 must be the same length. So that's the only possibility to have an equilateral triangle. You guys can check for the space diagonals. Well, obviously the space diagonals, they only connect opposite corners, so it's practically impossible for any equilateral triangle to have 3 of its sides equal to the space diagonal, to the length of the space diagonal. Anyway, so now that we know that for an equilateral triangle to be possible, the distances between the points must be equal to the length of the face diagonal. So apparently these 7 square root of 2, these must be the lengths of the space diagonal of the cube. So let's talk about one diagonal and how it is related to the side of the square. So let's focus on triangle DBC. So we're just focusing on 2D now because it is just it is just a triangle. So triangle DBC, we have a right angle here at angle BCD. So we can accordingly use the Pythagorean theorem. So let's just say we call this D for diagonal, which we know the length of, it's 7 square root of 2 based from the calculations that we have. So we know that S squared plus S squared, it must be equal to D squared. So D squared, it's 7 square root 2 squared, and 7 square root 2 squared, that's going to be equal to 98. Or we can just solve for S here, or we can just use the relationship between a side and a diagonal, since we have a 45-45-90 degree, a 45-45-90 triangle. Technically, these 2 angles are 45. So the ratio between a side and its hypotenuse, a leg and a hypotenuse of a right triangle, that's 45-45-90, it should be 1:2 square root of 2. So we can form that S times the square root of 2, it's going to give us 7 square root of 2. And with this, we're going to get S equals 7. Now, no worries, if you tried to use this one, you're going to get S equals 7 as well here, so no problems here. Right, now that we have the side, everything is done because the formula for the volume is the cube of its side, so 7 cubed, and that's going to give us 343 cubic units as our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!